So now we will give some example of the stability of the we'll give some example of the stability of the macrocom system.
Mr. Bean, do not swing.
Oh, so very good.
Distracting.
Okay. So
Make it slow. Got it?
so
Unstable, right? Too oscillatory.
I will begin with I will show the step will not even for the linear the stability or subsystem host does not imply the stability of the macrocom system and vice versa. So we give some two examples to demonstrate this kind of stability of macrocom system. In the first example, we see that we have the system, macrocom system have two modes, and the charging pneumatic is here. And now we see that all the system mode is stable. You can see because the negative part with the value of the magic A1 and 2. But the macrocom system is unstable.
What is red line and blue line?
Oh, this is the X1 and X2 in the state variable. Sorry, it's on my I forgot the notation. So and another example is that we have we also have the system with two mode and the system stable, system 2 is stable, but system 1 is unstable. You can see the system 1 is unstable. But the macrocom system is also stable if we can choose the global characteristic magic. So via the two examples, we conclude that the stability of macrocom system should be considered in the stochastic C. It is not the deterministic C. So now we're going to present the macrocom for this system. So by using the sector nonlinearity method. For about the complex set in the open space, so the nonlinear macrocom system can be used in the form of fuzzy models. So that's the equation. In the equation, the magic is B, E, C, D, E, C, D, X is the complex combination of those constant magic. And the theta is the fuzzy function satisfied the fluid constraint. So now we go to the control design problem based on the Leonard function. So now our control problem is that we have to develop the stochastic non-gravity stabilization, and further we have to we design the distributive performance. The reason for the develop the distributive performance is that the distributive performance including two case, that is the facility, and infinite performance. And in addition, we have to deal with the incomplete transition description. So here we have to decide the system into different steps. In three different steps. So, and lastly, we have to also develop the non-binary distributed compensation non-compensation. So, based on the control problem, we have we need to some challenging problem. The first challenging problem is the coexistence of the time varying parameters that is the time rate and so the basic function and is time relative, and because of this challenging problem, so we have to get problem that how to obtain the linear magic inequality based equation. The linear magic inequality has been solved effectively by using some famous numerical feedback for the complex optimization or the simple design programming. So then the challenging problem is that we do the design of the derivative of the basic function that will lead to the semi-global and local stabilization approach. So and finally, so the challenge our proposed method should be obtain the less conservative result than is it the result. visualization. So we do the mode depends specific by the controller that in the fully form. So now problem is to design the feedback magic FG. So based on this controller, we can obtain the closed system. So now we will review the definition of the stochastic release table. That is the solution of the Markov system converts to the origin in mean square in mean square scene. So now we would like to introduce the distributive performance. The distributive performance have been characterized by the quadratic energy supply rate. So by choosing some suitable magic QS or R, we can obtain the infinity performance and passivity performance from the based on the distributive performance. So now we will give us two types of Liouville function. The first type is the quadratic Liouville function or mode dependent Liouville function. That is the fully form. So to obtain the stabilization equation, we have to introduce the infinitesimal operation and generating formula, maybe to investigate the stabilization of the Markov system. So now we can obtain the parameterized linear magic inequalities based distributive performance in the lemma 2.2. In the lemma 2.2, there is a big problem that the coefficient of the Johnson rate and the feasibility function. So there's now a type of Liouville function for that is the non-quadratic Liouville function. The first step to use the non-quadratic Liouville function has been provided by Professor Kuhn. So now I will develop the work. So the non-quadratic Liouville function is the following form. So and you can see that. So why we call it is non-quadratic function, because the feasibility function is not also depend on the state variable. So that's why we call it is non-quadratic Liouville function. So in the same manner as the previous, we have the PMI by distributive coefficient in the lemma 2.4. So in this lemma 2.4, the most different here is the coefficient of three different kind of parameter. That is the Johnson rate, feasibility function, and this derivative. So now the problem is why we should choose a non-quadratic Liouville function, because you can see that there's the additional parameter. We don't want this, but why we choose this kind? The reason is now we go into another example. That is the autonomous fuzzy model. That is there's no control input and disturbance. So with the help of quadratic Liouville function, so we can obtain the sufficient condition for stability of the buffer. So if we use the non-quadratic Liouville function, we have this sufficient condition for stability of the system. So now here is the convert combination here, but the convert combination is equivalent to the x matrix is smaller than 0. X matrix is negatively 5. So in the double convert combination, this equivalent is not true. From the right we can obtain left, but from left we can swap to the right. So that is the reason why we had to choose the non-quadratic Liouville function. So now we first present one of the most famous results on the parameterized linear magic inequality based relaxation technique. That is for the double combination or double Fuji summation. So the most beautiful thing in the Riemann is that we can convert this double perfect combination into the linear magic inequality without any additional select variable. You can see there's no relaxation, there's no additional select variable to convert this PRMI into the LMI. So based on this, so in our problem we also develop another relaxation technique for the relaxed design of the Chinese grid. That is the following inequality. The following inequality has been answered by the lemma 3.4. And with the head lemma 2.4, we can see that the above the lemma 2.2 can be converted into the lemma 3.2. In the lemma 2, we have the stabilization condition, the instability condition or the stabilization condition formulated in terms of linear magic inequality. We can solve the specific magic. So there are now kind of pipeline linear magic inequality. Here is double pure lines. Here we consider the two types of the scalar, that is the theta I and nu k. So that is that they find the following constraint. So this our relaxation technique here is to answer this kind of this inequality by using the lemma term lemma 3.6. So now we want to introduce what the semi-global stabilization. The semi-global stabilization is that first we have to assume that the time derivative of the time derivative of physics function is bounded. So based on the assumption, so we see that the lemma 2.4 with the POI with the Chinese grid physics function and is the time derivative, we can realize by the lemma 3.4, and using the lemma 3.6 above, we can get a theorem 4.1. Here is this distributive condition formulated in terms of LMI. So in the case of there's no disturbance, we can obtain the curve 4.1. So there is the non-PDC scheme that we will introduce later. That means above also. So the most the obvious advantage of this our proposal method is that our proposal method requires the less number of discrete variables compared to another research, and we see that the theorem 4.1 is semi-global stabilization, and the result in 48 is semi-global stabilization, but the result in 39 and 47 is global stabilization. So now we will introduce our main result, that is global stabilization. So and you can see that from the whole semi-global stabilization, we have to assume that the boundary on the time derivative of the basic function. So now, but the time derivative of the basic function is not only depend on state variable, but also depend on the control input and undistributed WT. So this assumption is not practical. So now also it is necessary to exclude the assumption by using our local stabilization approach. So for investigate local stabilization, we first we modify the spring stability in the definition one by adding the local condition. That is for the initial state starting from the local stability region. So the solution of the maximum system also bounded by in the operation region. So here we also give example, we modify the definition of infinity performance. So that we also add the local condition. So now we have to make assumption that the control input and the disturbance has bounded energy that is satisfied with flow equality. And here is our very important results on local stabilization. That is the lemma 4.1. So for the easy understand, so now I can explain the lemma 4.1 by using the figure 4. For the first inequality, the first inequality guarantee that the solution has been converged to the origin in mean squaring. So the second inequality ensures that the origin ellipse lie on this side the operating region, and the third inequality maybe ensure that the local stability region belong to the intersection of the green and blue ellipse. So here we also have the present of the time derivative of the basic function.
We use the different symbol, the less than great than
Okay, thank you. So this symbol is for the magic. That is it was scalar. That's why we have to do different notation.
positive
The positive and the magic. That is the scalar. That's why we should
Is
use
it the general accepted
the
way? Is that right?
yes, right.
But most of the they do not differentiate, right? 이렇게 그죠?
So we use
이퀄리티를 다르게 안 쓰듯이.
so we use this guy for the
Okay, anyway, okay, just for notation.
They only to make a lot of the notations that makes some readers confused.
understand. So it was
So many symbols, even in equality, makes confusion. Okay, it's minor.
So now we use the lemma 4 maybe to describe the convoluted and basic function. Now, and you see by using the property of the secondary methods, we can describe the convoluted of the basic function in Fourier form, where this is where the var is a weighting function, and x dot is the dynamic system just over. So now we have to, based on this lemma from 2, we have to make the assumption 2 like that for all the x in the for all the in the operating region. So in addition, we also developed an additional relaxation technique. So that is, can we see that it is the present of the convoluted of the divergent functions. So now we develop the relaxation technique for this kind of inequality. That is scalar. That is scalar because this scalar. So you can see we can refer the lemma for 4.3 for the some relaxation technique. So yeah, the lemma 4.2 formulate is equality in terms of parameter lemmatic inequality. So now we will sketch now. We will describe the proof of the theorem 4.2. So that is based on the theorem lemma 4.1. It exists the three kind of different primary parameter. So we can obtain the PMMI. So we can obtain the LMI's based any condition in theorem 4.2, and we can obtain the corollary 1, the corollary 4.2 in the case of there's no disturbance. So now we go into some example to show our advantage our project methods. In the first example, so in the first example, we can see we compare the feasibility reason obtained by our method and proposed method. Because the system the market for this system there's no disturbance and with formal and true physical rules. So here's we add the number A and B to generate the feasibility reason. So here's this Chinese magic. So for the local stabilization approach, first of all, we have to define the operating reason of the physics model. So based on the operating reason, we can select the previous variable, and we can select the weighting function and feasibility function. Yes. So based on this setup, we can obtain the assumption 4.2, and we can solve the corollary for 4.2 for obtain the 50 again magic. So now this is my first. Now this is our comparison. So as we can see in the figure 5. Yes, so as we see in the figure 5, here is the Lagrange stability, the Lagrange feasibility reason provided by our proposal in corollary 4.2. You may see. So the second Lagrange is the corollary 4.1 when we propose the stability rules reasonable, and we see that when we increase the bounded assumption on the time derivative, you see the feasibility reason obtained by Sydney Global Stability Support. Here we go is the corollary 4.1 and this 448. The feasibility reason is reduced. So, but for the global reason, for the global stability approach and local stability approach, we don't use this kind of assumption, so we don't have any impact on this. So now we will check whether the assumption is true or not. So now we take a simulation. So and we see that the actual time derivative of the feasibility function is over the assumption, the assumed assumption. That means this Sydney Global stability approach is not true in this case. So to using the Sydney Global stability approach, we have to increase, and we have increased the boundary on time function. So luckily when the time function we get is high, this is the reason. So however, in the local stabilization approach, we can see that on the we see that here is the local stability reason. So for every initial value we rely on the boundary of the reason. The solution also converges to the origin. So and all solution lie also inside the operation reason. You see that. That is our corollary 4.2. And another example is the nonlinear mass spin number mechanical system. So in the same manner, we also choose the local operation reason C, and also choose the previous variable and weighting function and feasibility function. So we also have this assumption 4.2 for the sigma 1, and based on this setup we can solve the theorem 4.2 to obtain the feedback gain matrix. The difference between this assumption and above assumption example, in that this assumption consider in the place of there is a disturbance. No, sorry, I missed the disturbance here. So now we can give we show the comparison of this disability performance level. So and we can see that we have the three approaches: global, semi-global, and local stabilization approach. So in global approach, we also develop the Tailwind 3.2 and the Tailwind 3.1 also provide the smaller infinity performance. So also require the less number of scalable variable. And in the semi-global approach, so I compare our Tailwind 4.1 to the existing result in the 48. So let me see that we also can obtain less conservative result here. So now we will consider the local stabilization approach. In the local stabilization, we will see that we don't have this assumption. Can you see that? Global logic assumption and global logic assumption. So, but our performance also better than the global approach. Can you see that? This model infinity performance is better. So, and we also require the less number of scalar variable. Yes. Here you see that the quadratic level function will be designed in the global approach. So any non-quadratic level function will be designed in local and semi-global approaches. So here we show some step response of the semi-global approach. Let me see that the step response will converge to origin, and see that the time derivative of physical system also spawn on 5. That is our assumption. So here is solution. Here is the step response when we use the local stabilization approach. Here is the effective performance. So for the effective performance, so we should step the step in origin. So under the impact of the disturbance, so the step go out, and also when we move to the convert to origin. And here we check the effective performance. That if it is smaller one, it is true. So here is local stabilization approach. Here is we obtain the local stabilization here. If we set the step, we set the initial step on a boundary under the impact of the disturbance, the solution go outside and also go inside and can converge to origin. Here is the state response. So in conclusion, we have the two main conclusion here. The first conclusion is this presentation improved the existing result of semi-global non-quadratic stabilization of the non-homogeneous quantum system. And another thing is we also developed the theory framework for local non-quadratic stabilization of the non-homogeneous quantum field system. So here is our publication. Our main result comes from this the publication 1 and 5, and here is our conference. So that is our presentation. Thank you for listening.
Okay, thank you.
First, it is a minor question. 28. Next is page. the number of Scala variables, the
Yeah.
tables of previous page. And there are 3 references.
Yes.
Yes, but this table contains only 2 references. So why one is one of one?
Thank you for the interesting question. So, because I see if we add one more notation here, so we don't see anything. Because I just only add 4. So if we add 5, I think I have no chance to be explaining.
Yes.
I have a related question. So then, did you think whether it is some effective way to illustrate? Because if we add more, then we cannot compare. Then it's not the way, I think.
So
Every A and B are integer.
then we will
Okay.
for easier.
Is there any other way to compare?
I think there is there's
This is the best way we ever.
I think there is
No.
I think I have maybe one more method. If we just add if we just draw the heights,
So we just need a boundary, right?
then we use the left arrow.
Why you are trying to fill the gap, fill every space?
So
Do we need a shade or something?
this is my focus.
No. I'm not saying about someone's work. So I think this paper also published. I think the reviewer agreed, but at this time we can think about it, think over whether it is a good illustration to compare them or not.
So we can use former on other existing results.
그때까지는 3개인데 어땠죠? 이 친구 4개 하면 아마 5번째부터는 기분이 안 나. 여기 다른 건 없어요.
Next page.
Next page.
Next page. Similar question the previous presentation. I think the mode evolution is related to the transition matrix, is that right? So how you generate the mode evolution? Because the non-homogeneous subsystem has completely unknown transition rates, right? So how to handle?
Thank you for this. Actually, in the simulation, we given the Jackson rate of the simulation. So, but we don't use this for the solving the Curry formula. Just use the given.
Same mode evolution. Yeah. So do you have any idea to generate the mode evolution? Do you have any idea to generate mode evolution with completely unknown transition rate? Any idea?
Actually, I have no idea.
One more question. So you also reduced the number of Scala variables, the previous students saying. So same technique. How to reduce the number of variables? The same technique of previous students or not?
This is my lecture technique in the chapter 3. So now we will take a look at the previous research and the job research. So in previous research, you don't use the parameterization, parameterized distribution. So that's why your result will be have there's a lot of you require a lot of Scala variable. in our approach, because the probably use the PMI business capability, so that I will review maybe a lot of Scala variable. So, and for the better performance, that is when we use exposition, so we can use a lot of slash variable, but how much is not really easy to answer. It is not question to easy answer. So by using the PMI technique, so we can reduce the number, large number of Scala variable, and also get a better performance.
In your presentation, you used only two-dimensional system in all your examples.
Yeah.
Did you check the three-dimensional system or other system?
Maybe I have not. I do not use for the three-dimensional system. Like I think maybe is my message or my fault.
Why you use only two-dimensional?
Okay, thank you for the question. So because the two-dimensional system is very easy to describe trajectory. Yes, we can describe the trajectory in the plane. So in the three-dimensional system, the trajectory is not in the plane, is in the 3D figure. And moreover, the use of a three-dimensional system will reduce a lot of problems. We will require a lot of time to solve the real-life problem. So that's why I use the two-dimensional system for easy to understand. That's why I just always consider the two-dimensional system. Thank you for the question, also.
Maybe it is nice to compare to previous years.
Yes, because the result of the lesson, but just only use two-dimensional systems.
In your research topics, we focus Markovian jump body system. Yes. Nonlinear Markov jump system in page 8. You use the sector nonlinear method, and it can formulate the nonlinear Markov jump system into nonlinear Markov jump body system. Yes. What is the sector nonlinear method?
Okay, thank you very much. So I will briefly describe the sector nonlinear method. The sector nonlinear methods come from the factor. So here is we get a lot of non-nonlinearity in this equation. So in the sector nonlinearity or sector nonlinearity, so we assume this nonlinearity is bounded in some linear section. So we can by using assumption on all the system mode rely in the boundary compact set. So we can establish the nonlinearity sector. So by using this, so we can establish some weighting function. So that's why we obtain this method of this system by using sector nonlinear method. So that the detail give in mind